We've seen in a previous video that we can generate the cosine function using the Taylor series expansions. Now that's not necessarily the way that we want to do it. In fact, there's a simpler method here. We can generate the cosine function from the sine function. So in order to do that, we use this little identity. So the cosine of a value x is the same as the sine of pi by 2 minus x. So let's say, for example, we're dealing with it in degrees. So let's say we look at the cosine of 30 degrees. That gives us 0.866, which is root 3 upon 2. Now to generate this, what we could do is, instead of trying to generate the cosine function, we can just generate the sine function. But it's the sine function of a different angle. So the angle we want to do is pi by 2 minus x. So pi by 2 in degrees is 90 degrees. So it's 90 minus the 30, which is a sine of 60. And that is the value 0.866. So you can see these in the graphs above. We have the sine function in blue and the cosine function in brown. Now we want to generate the cosine of this angle of 30 degrees. And that's this point up here. So it's pi by 6 in radians. And the value is 0.866. But that's going to be exactly the same as this height here on the sine curve. So if we click on that there, this is going to be the pi by 3, and you see the height is 0.866. So in order for us to generate the cosine function, all we need to do is use the same code for the sine function, but we just change the value that we put in. So for example, if we want to generate the cosine of 30 degrees, what we do is we change the 30 degrees into 90 minus 30, and then we put it into the sine function. And we generate through the sine function, and we pop out the result, and it will give us the cosine over 30 degrees. So nice and simple. And in fact, that's the way we're going to go forward with our cosine function. But we will still leave the Taylor series approximation subroutine sitting in the ROM. It's doing no harm sitting there. We've got plenty of room for it. We just need to call this subroutine a different name. So let's go ahead and we will look at the subroutine now. On the right hand side we have the calling function. On the left hand side we have the subroutine. So all the calling function does is push a value of x into the cosine subroutine. Now I've called this cosine subroutine cosine shift. So it's going to pass the value of x. Now the value of x I have here, so this is in radians, so this is actually 30 degrees. Now in order to work out the cosine of this function, we're going to have to work out pi upon 2 minus the 30 degrees. So whenever we do the pi upon 2 minus the 30 degrees, we get 60 degrees, and 60 degrees is this actual number here. So this is 60 degrees in radians. And whenever we work out the final value of the sine of this, we're going to get 0.866, which should be 00 dd. So the cosine of 30 degrees should give us 00 dd. So we're going to pass this value of x into our subroutine. So let's have a look at the subroutine. Now in the subroutine, we're going to pop the value off. So we're going to take the value of x, which we just passed in, which is our 30 degrees. So we're going to pop it off into register R0. We're going to put the value pi by 2 into register R1. And then we're going to generate R0 equals pi by 2 minus x. So that's what this line does. So now we've got the new value for our value of x, which is the pi by 2 minus x. We can push this, the content of register R0, so we push this value back onto the stack, and then we can call the subroutine for the sine function. So we run through the sine function. Now I'm not going to bring that up because we've seen that previously. So we run through the sine function, and then once the sine subroutine has finished, it will return the value onto the stack. So then we can just pop that answer back off of the stack into register R0. And that's us got our final answer. and then we can push that value into the cosine shift onto the stack, and then we can return to the calling function. So we return up to the calling function here, and once we've returned up the calling function, we can pop that value off of the stack, and that'll be the end of the program. And hopefully within the memory location cosine shift underscore x, we should have the value of our 0, 0 dd. So let's go ahead and I will load that into the CPU and we will see it running. So I have put the code into the RAM and the subroutine into the ROM, and this is it running up now. It takes a couple of minutes for it to run through, so it's been running for about a minute so far. So why don't we have a little look in, because not very often do I take my time to have a look into the actual circuitry here. And a lot of people who maybe are just having a quick look at these videos might be thinking this is all we've got, just the top level, but we have in effect got an entire working CPU. So we have the CPU here, we have our ROM, which we use in order to contain all of our subroutines, and we have our RAM, which we use in order to contain the code and also the data for our programs. And we have a keyboard, display, graphics unit 1 and 2, and a couple of spare IOs. So when we drop into the CPU, you can see the CPU, we've got the ALU, we've got our registers, we've got an accumulator, an instruction address register, memory address register, and the control section. The control section is part hardwired and part microcoded. So you can see the counter here is running through and it's counting along these lines. Now, halfway down here, you can see on the left hand side we have all of the enables, and on the right hand side we have all of the sets. The microcoded control unit is in here. So that has a compression ROM which picks out particular micro instructions, and then it jumps to that micro instruction, runs through the micro instruction, and then jumps up to the next value for the ROM, and the ROM picks the next micro instruction. And you can see here the micro instructions are actually heading off to all of the sets and all of the enables in the upper level. So if we head back into here, we can see that we have the ALU as well, and the ALU is running away here, and we've got all our different options within the ALU. So a shifter, shift left and right, not and or, exclusive or, an increment, a decrement, a multiply, divide, and also a comparator, a subtractor, and there's a test here as well, a separate test here as well for 0. So that's the basics of it, and when we come up to the top level, we've got our display, a keyboard, a graphics unit, and we have all of our flags brought up to the top level. We have our control unit, and we have the position of the clock. And we also have an extra trap here as well, which works through and tells you whether there's any errors within particular pieces of code. And then we have all of the registers brought up here to the top level. So R0 to R5, the stack pointer, an index register. This is actually, it's called FPU, meaning floating point unit, but it is in fact just an extra register we've got access to. Instruction address register, instruction register, and the R6 temp. So this is a register that is only available within the control unit for generating microcode instructions. So that's it finished anyway. Let's now stop the program and we will go in and have a look and see what the final result is. So if we head into the RAM, now we were looking for the answer 00DD, which would have been 0.866 or root 3 up and 2, so that would be the cosine of 30. But we've actually got 00DE, So again, we are 1 unit out, but we're not very far out. So we've got a relatively good approximation for this particular value. So that shows that we are able to generate the cosine function, the cosine of an angle, by actually using the sine of the angle, but using the pi upon 2 minus that particular angle. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.